Perfect. Okay, so our last speaker before the poster talks is Fei Dai. So Fei, you're presenting virtually, right?
Yeah, I'm here.
Yes, there you are. Okay, great. So Fei is a postdoc at Caltech, and he's going to tell us about a resonant chain of exoplanets only 600 million years old.
Thank you. Hi, everyone. My name is Fei Dai. I'm currently based at Caltech. Sorry, I can't be here in person this week. I'm actually at a meeting on the East Coast. So for those of you who do not know me, I usually study exoplanets that are very extreme, that look nothing like our solar system. And the hope is that using these extreme planetary systems, we can understand the missing links in our traditional planet formation theories. And today I would like to highlight one of such systems that we discovered recently. All right, a key prediction of modern planet formation theory is that planets migrate as we grow in protoplanetary disk. This is due to the gravitational interaction between the planet and the disk. And in most part of the disk, the net effect is for the planet to migrate towards the central star. Now, if you have multiple planets forming simultaneously in the disk, the heavier planets tend to migrate faster than the lighter planets. And you have this differential migration. So before the planet collide into each other, they usually are caught into a so-called mean motion resonance. And mean motion resonance refers to a configuration where the planet orbital period are near some small integer ratios. Here, the mutual gravitational perturbation the planet have on each other can be accumulated over multiple orbits. And this resonant interaction effectively acts as a potential well that traps planet in resonance, and while both of them are moving towards center star. And this process can be extended to capture a series of planets into a resonant chain, as shown by the histogram on the left, by the schematic on the left. All right, so this process of resonant capture is considered to be so effective and robust that it is almost surprising to us that if we look at the mature planetary system, only a small set of them are currently found in lower order mean motion resonance, as indicated by the vertical dotted line. In the Kepler sample, only a few percent of these systems are currently near resonance. And if we look at them more carefully, these near resonance system still shows 1 to 2% deviation from mean motion resonance. So several theories have been put forth to resolve this tension between disk migration, which consistently form a series of resonant planets, versus the observation of mature planetary system, which consistently lack resonance. So one possibility is tidal interaction with the host star. Over many giga-year timescale, the tide can move a planet off resonance. Or it may be giant impact collisions, which is very violent and can totally disrupt the initial orbital architecture of a planetary system into a non-resonant configuration that we see today. And planetesimal scattering is somewhere in between. It can either move the orbital periods, or it can also cause overall instability to the host system. So that sets the stage for the new system we want to discuss today, QI1136. The system is a young sun-like star that hosts at least 6 transiting planets. And hopefully by the end of the talk, I will convince you this young system still records the initial condition from this migration. So according to the test light curve, there are at least 6 transiting planets with orbital periods from 4 days up to 40 days. And the planets are nicely in a resonant chain with an orbital period ratio of 3 to 2, 2 to 1, 3 to 2, 7 to 5, and then back to 3 to 2. So one thing we know pretty sure is that the system is young. From a combination of gyrochronology, which is measuring the rotation period of the host star, lithium absorption, as well as chromospheric activity, our best age estimate for the star is about 700 million years. This is much younger compared to the mature Kepler planetary system, which has a median age of 4.6 giga-year. And I mentioned earlier, the near resonant Kepler systems are typically 1 or 2% of resonance. However, if you look at TOI 1136, which is indicated by the red line or the red points here, their deviation from perfect resonance is at about 10 to the minus 4 level. This is much steeper in resonance compared to most other exoplanet systems that we know of. It was perhaps no surprise that we detected strong transit timing variations on all 6 planets, given the deep resonance. The deep resonance greatly amplified the gravitational interaction between the planets, and the orbits are no longer perfectly periodic. And it turns out, by modeling the TDVs, or transit timing variations, there's a lot we can say about the orbital architecture of this young system. All right, so so far we talk about resonance in terms of pure ratio. However, perfect integer pure ratio does not guarantee true resonance. The hallmark of true resonance is the libration, or simply the oscillation of a resonant angle with some small amplitude around a fixed point. And the opposing case is circulation, in which the resonant angle explores the full 360-degree range. So what is a resonant angle? Well, a resonant angle is nothing more than generalized coordinates for the resonant part of the Hamiltonian, and it's given by the sum of the mean longitudes of neighboring planets. Rather than going to the math, let's examine the geometric significance of a resonant angle. Let's look at this, my favorite video from Wikipedia, which shows the resonance of the Galilean moons. So we know Io, Europa, and Ganymede are in a 1 to 2 to 4 mean motion resonance. And their resonant angle, shown here, actually librates around 180 degrees with a small amplitude of just 1 degree or so. And this libration of resonant angle actually dictates that whenever 2 satellites have a conjunction or close to each other, the third satellite is either 180 degrees away or 90 degrees away. So the libration of the resonant angle precludes triple conjunction between the satellites and prevents chaotic interaction between the satellites, and thus promote long-term stability. And we believe a similar situation is happening on TOI 1136. On the left, I'm showing a ladder of resonant angles involving increasingly more planets, from 2 planet, 3 planet to 4 planet resonant angles. And the numbers in the brackets indicate the fraction of a TDV solution in which the particular resonant angle is in libration. And you can see for the low order resonances here, they have almost order unity of probability of being in resonance. And on the right, I'm showing the time evolution of a typical TDV solution we found. And you can see the various resonant angles librate around 180 degrees, just as we have seen for the Galilean moons. The only exception is planet E and F, which are highlighted in red here. The planet E and F is the only case of second order resonance here in this system. And if you look at the time evolution, the gray color points, the resonant angle is kind of chaotic. It can change from a state of libration into circulation and then come back. So what is so peculiar with the second order resonance? Well, first of all, the order of the resonance is defined by the difference between the small integer. So 7 minus 5 is 2. This is second order. The other resonance here, 3 to 2 and 2 to 1, are all first order. So if you open any textbook on selection mechanics, it will probably tell you that second order resonance is much weaker compared to first order resonance. It is suppressed by another factor of orbital eccentricity. And for most planets we know, the orbital eccentricity is typically a few percent. So that represents at least 1 order of magnitude suppression in strength. Moreover, let's examine the width of the resonance, as shown on the right, in terms of semi-major axis versus eccentricity. And we can see the first order resonance, 2 to 1, 3 to 2, they have substantial width in semi-major axis. Whereas the second order resonance, 3 to 1, it is razor thin in semi-major axis, especially towards small eccentricity. So the bottom line here is the second order resonance that we see in TOI 1136 is much more challenging to be captured into during this migration. due to both the weaker strength as well as the thin width. You can imagine if the disk migration were fast or turbulent, it can easily skip the range or the realm of second order resonance. So our insight here for this system is that we can turn around this difficulty in forming a second order resonance around and turn that into a strong statement about the kind of disk that gave rise to TI 1136. So we carried out a series of disk migration simulations. I don't have time for the details, but the key result we found is that we have to put an inner edge of the disk into our simulation so that all the planets nicely capture into their observed resonance, including that second order one. So in reality, one would expect the disk to have an inner edge, at least due to the truncation of the host star's magnetosphere. And the resultant pressure bump at the inner edge actually provides a natural way to slow down migration or even reverse the torque applied on the planet. And very curiously, the innermost planet we observed, planet B, is actually on a 4-day orbit, or in terms of semi-major axis, just 0.5% of AU. And if you ask your disk expert friend, they'll probably tell you that this is exactly where we would expect to find the inner edge of the disk. So here we're showing time evolution of the period ratio, the eccentricity, and the two-body and three-body resonant angle in a typical disk simulation we had for TI 1136. And we can see on time scale of tens of kiloyears, all the 6 planets can be clicked into their observed resonances. By the way, this is much shorter than the 3 million year typical lifetime of a protoplanetary disk. Moreover, when the planets capture into resonance, their resonant angle change from a state of circulation into a state of libration, just as we have seen for the Galilean moons. Another result we found is that in order to form a system like TI 1136, its disk has to be less dense than our solar system's disk. If you look at the minimum mass solar nebula, it was estimated to have a surface density of about 2,000 grams per centimeter squared at 1 AU, indicated by the orange line here. And in our successful disk simulations, shown by the blue points, the disk that formed TI 1136 has to be less dense than our solar system. And the low density was required to slow down the migration, particularly to capture the system into a second order resonance. So this is a KEC science meeting. I want to mention one KEC result we found for this system. We actually went out to measure a Roster-McLaughlin effect for the largest planet in the system, shown on the right on KEC Iris. And the result indicated a well-aligned orbit for the system. Moreover, the transit time was exactly where we expected from the TDV model, confirming the strong TDV that we see in the test light curve. So the well-aligned orbits, the coplanar orbits in which all 6 planets transit, are actually both consistent with the very delicate resonant configuration. If the planetary system were misaligned with respect to the host star, then different nodal precession would again try to cause instability and maybe even disrupt the system. With that, I'll leave my summary slides, which I borrowed from Sean Raymond. So the current paradigm for small planet formation is that planet embryos grow and migrate in a disk, and the end game is usually a chain of resonance anchored at the inner edge of the disk. But if we look at mature planetary systems, the vast majority of them actually go unstable and have their initial resonance disrupted. So TI 1136 nicely come into this picture by filling the gap between disk migration and the mature planetary system. It is a primordial system that still records the initial condition that we have from disk migration, and may very well be the precursor of many of the mature multi-planet systems we know from Kepler. All right, with that, I'll end here. Take any questions?
Thank you, Faye. Yeah, are there questions in the room for Faye?
I don't have any hands in here, Steph.
I have one quick question. So I would guess, systems like this would be rare just because of time scale. I'm curious if
Yeah.
there are others that would be useful for tracing the conditions of migration. And if there aren't, how many you might expect to be able to find.
Yeah, there's one other system, V1298. I think Lin was part of the discovery of that system. It's also a multi-planet system. It's young. I forgot the exact age. I think younger than 100 million years even. There, the orbital periods are less well known because the period are longer, and it was observed with a shorter mission, K2, only had 80 days of observation. So we are less certain about the orbital period there. But that system indeed also show TTVs, transit time variations, which again is at least indicative of near resonant configuration. So yeah, I hope more follow-up observation, photometry from the ground can tell us better what that system looks like.
Cool, thank you.
Perfect. And our time is up. So thank you very much.